Hi, everyone. Thank you for joining us to discuss the fascinating topic of transforming large language models, or LLMs, for HPC codes and tasks. I'm Galoran, and I'm from the Technion and NRCN. Today, we will explore how domain-specific LLMs can revolutionize high-performance computing. Before we dive further into our research, it's important to highlight that this work is a result of an incredible collaboration. We have had the privilege of working alongside experts from Technion, Ben-Gurion University, Intel, and Intel Labs that share our passion for advancing high-performance computing and AI. Also, this work could not have been carried out without the generosity of our sponsors, especially in hardware support. One more thing before we start, this presentation is based on a 2023 continuous effort, all of which is online and open sourced. In this talk, we will also share some new exciting results and create an internal logic between the interconnected works. I will start by presenting the background and objectives of our work in LLMs for HPC. Then Niranjan will present our novel HPC code database, HPCorpus, which we used for our work. After that, V will showcase ToCompiler, our novel tokenizer for compiler-oriented tasks, and the pre-training perplexity results on our CompCoder model. Lastly, Tal and Nadav will demonstrate how these models can help in downstream tasks for HPC, such as OpenMP and MPI classification and generation. Well, it's not a secret that LLMs are the new frontier in AI. Those ever-increasing scope models trained on infinite data with extended data representation using large-scale supercomputers can perform enormous amount of tasks given their knowledge fusion, from writing poems to coding Python scripts. This booming trend gave us all sorts of models. If we focus on GPT models as a building block, it's not a shock that early experience with state-of-the-art GPT-4 is now considered a spark of general artificial intelligence. Narrowing down the talk to our interest in code, those models are getting better and better at doing all sorts of general code intelligence tasks, especially when we ask them in our natural language to generate or act on code. But when we asked ourselves, can those models work well for HPC code tasks, we got a little bit confused. If such tasks target the compiler and the hardware, and there is no meaning at all to natural language in this or to any other human semantic when considering performance, how general purpose code models can even help? Are those trained for this task, or will they just act to please our request given such a task without understanding it? And if to be specific, when transitioning from the general purpose code task that we mentioned before, we can now clearly see that the relevant ones in HPC codes are not the same at all. How, for example, can an LLM help me sort out problems with the data flow without getting the data flow graph? How can it sort out what exactly is happening without the AST? That is why we dug into the code models and trying to find what can help us with HPC codes. Our main concerns remained: can non-HPC language, which all of those models are trained on, be the baseline for HPC tasks? Are there any relevant large corpora of high-performance code out there? What are the exact downstream tasks for HPC? And how can we correlate those with the common models? Is mixing of languages and tasks even good for HPC LLMs? When we looked carefully at how those models were pre-trained, we also asked, are common tokenizers even relevant for compilation-oriented codes? What is the relevant model architecture for HPC task learning. And when we started to understand that we will need to take all of those considerations into our future new HPC LLM training, we also wondered, should we consider other representations rather just plain code or AST? What about hardware specs? Telemetry? Should it be part of the input? Can we reduce the size of the input, of the models, of the training? So many open questions. That took us to the conclusion that in the case of HPC LLMs, there is no generality. If we want to transform LLMs actually to help with such tasks, scope is what we all need.
Thanks, Gal, for the introduction. Hi, everyone. My name is Niranjan. I'm a research scientist at Intel Labs, looking into applications of AI towards software engineering problems, as well as high-performance computing. Today, I'll be talking about HPCorpus, which is our novel HPC code database. Now, as Gal mentioned, training large language models requires a large amount of training data. And that was the whole reason to build HPCorpus so that we can train an LLM for HPC applications. The first question that we had to answer as a part of building HPCorpus was selecting languages. Specifically, we looked into recent research published at ISE23, as well as the software stacks for Frontier and other supercomputers. And we found that C, C++, and Fortran are the three most dominant used code languages by HPC applications. Also, top HPC applications use MPI for distribution as well as OpenMP for shared memory parallelism. They also use GPU offloading. So we decided to use these three commonly used programming languages to mine GitHub repositories on open source software and build HPCorpus. Another interesting question that we had to answer as part of HPCorpus was whether to train an LLM from scratch or to train or fine-tune an LLM, or existing LLM that is pre-trained on some other languages. Towards that end, this particular research paper shows an interesting insight. On the left-hand side, you see the pairwise similarity between different programming languages that are pre-trained, not pre-trained setting, meaning the codebird model was trained from scratch on all these languages. And what we see is that C++, Python, C, CUDA, and Fortran are quite close to each other in terms of their token representations, whereas assembly, COBOL, and R are further away in terms of their token representations. But if you compare that with on the right-hand side, which is a pre-trained setting, meaning CodeBird was pre-trained on Python, JavaScript, Java, Go, and R languages, although the overall observation is still the same, you can see that the representation for languages such as Go, which was part of the pre-trained set of languages for CodeBird, the similarity has changed. What that means is that if you train a language from scratch, train a model from scratch versus fine-tune an existing model could have a significant impact on the representation of the tokens used by languages. So given this observation, we decided to train an LLM from scratch using HPCorpus. But I'm not going to cover about that right now. That is going to be covered sometime later. So giving more details into HPCorpus. So HPCorpus consisted of all C, C++, and Fortran codes from 2012 to mid-2023. At a higher level, it consisted of 3,300K repositories, around 70 gigabytes of code, 9 million functions and 9 million files and 155 million functions. You can see the distribution or the breakdown of these statistics between different languages on the right-hand side. We use Google BigQuery and particular code shown on the top to mine open source repositories. Specifically, we looked into different file extensions and use those along with appropriate licensing to ensure that we mine open source code that is license friendly also. We have presented the analysis or the statistical analysis of HPCorpus into a research paper that will be published in HPEC, the High Performance Extreme Computing, towards end of this month. So feel free to check out the paper in case you're interested to understand more details. The link is towards the bottom of the screen. Just to give you some brief ideas about the paper, the first observation that we had was with respect to the usage of parallel programming APIs across repositories. What we found on the left-hand side graph was that around 45% of the repositories that are using parallel programming APIs use OpenMP. So essentially, OpenMP is the dominant parallel programming API across high-performance computing repositories. On the right-hand side, you see the distribution of these repository usages over a period of time. And what we found was that both OpenMP as well as MPI are still continuing to gain usages than other APIs such as OpenCL or SYCL, which is recently introduced. We have also further details in terms of OpenMP and MPI usage together and their further breakdown, because we found that certain applications use MPI and OpenMP together. But what we found was that OpenMP is still the most commonly used API than OpenMP and MPI together. And towards the bottom of the screen, you can see that we see a distribution of OpenMP APIs across different versions. What we found was that OpenMP version 2.5, which is typically called as the common core, is still quite heavily used as compared to recently introduced versions like version 4 and version 5. We have further details in terms of attributes that are typically used for loops as well as scheduling attributes. We found that static is the most commonly used scheduling attribute as compared to other recently introduced attributes such as auto and guided.
Hi, my name is Faye, and I'm an AI research scientist at Intel Labs, working on language models. I'll be talking about our efforts to pre-train models, and specifically work to develop a tokenizer that is better adapted to HPC tasks. So a bit of background and context. We first investigated whether we could use pre-trained code LLMs for our HPC purposes. However, these are all trained on a mix of programming languages, as you can see at the bottom of the slide here. This includes Java, Python, and Haskell, for example. This code is then all passed through the same tokenizer, which converts things, individual tokens, such as words or variable names, into a high-dimensional token embedding. And these embeddings are then passed into transformer layers. Now, very briefly, you can see that in the middle figure here. The task of the language model is to take an input and predict the next token in the sequence, or predict some masked token in that sequence. For this natural language example, the LM processes "the chicken walked" and should predict "across" as the next token for the full sentence, "the chicken walked across the road." LMs are trained on this sort of prediction task, and then their performance is measured with something known as perplexity, which you can see at the top here for various programming languages and various open source models. But we wondered whether we really needed the model to be trained on things like Java and Python if we wanted it to perform HPC tasks. This could cause the model to actually learn counterproductive constructs and generate incorrect syntax. So we aim to pre-train our own models using a domain-specific tokenizer, which I'll describe shortly. This should increase performance, but may even provide efficiency benefits. Now, current tokenization strategies that were developed for natural language have flaws when you apply them to source code. So you can see here on the left, GPT-3 tokenizer applied to source code. And one of the clear issues is that each individual whitespace is counted as a different token. Now, OpenAI fixed this when they developed a tokenizer for their code LLM, but this tokenizer on the right here is still doing things like splitting this number, 2800, into two individual subtokens. Now, in general, LLMs don't understand numbers very well at all, and this sort of tokenization splitting of a number is likely to confuse the model and generate incorrect predictions about the function of that number. So for TokenCompiler, we wanted to maintain the overall structure of the code, but to randomize the local semantics, such as specific variable names or numbers. So what we did is we generate replaced code, which you can see at the top here. This should encourage the model to use the structure of the code rather than the specific semantic content of the token to predict the tokens in the sequence around it. And to make sure we only kept functional code rather than things like natural language comments, we used an AST parser to go through the code in our corpus and only keep the functional code in a structured block. So you can read the details of all of that in our preprint, but the most important takeaway that I want to emphasize is that ToCompiler ends up having a very small vocabulary. For Fortran, this ends up being just over 1,000 tokens. This includes a couple hundred primitives and allows up to 1,000 unique different variable names or different numbers. You can compare that to a typical LLM vocabulary size of 50,000. So when you have a larger vocabulary, you then will need a larger token embedding layer and therefore a larger model. This can lead to inefficiencies during training. So we first pre-trained two different LMs, polycoder and SPT code, on Fortran. And we measured the perplexity of the model when it used the GPT tokenizer, which is known as BPE, or ToCompiler. And you can see that the perplexity is significantly lower with ToCompiler, indicating an average increased performance of 230%. And because the embedding is smaller, the models become notably smaller and reduce the overall training time by about 10% on average. For example, you can see on polycoder that the model size is decreased by about half. And here are our initial results for polycoder pre-training on C and C++, which is a much larger portion of our corpus. We began with a 3 billion parameter architecture because that's about the minimum model size that the literature indicates becomes useful for downstream tasks with other code elements. ToCompiler again improves over the BPE tokenizer, but interestingly, a smaller model actually maintains or maintains similar or better performance. And previous research actually indicates that we should scale the size of the model to the number of tokens of the training set. And since ToCompiler reduces the number of tokens, we found we could reduce the model from 3 billion parameters all the way to 638 million. So next, we plan to evaluate these coded LLMs on downstream tasks such as OpenMP parameter generation.
Hi everyone, my name is Tal Kadosh and I'm a master's student at Ben-Gurion University, and I hate to manually parallelize serial codes, especially legacy codes, as I find it to be very challenging, and I believe that many of you would agree. Not only that, the developers should know the overall intent of the program, but they must be familiar with the finer details, like how the variables can affect each other while executing the code in parallel. So in order to ease this process, we are examining the possibility of using large language models to automatically parallelize serial codes. This task possesses multiple challenges. First, the model needs to determine if parallelization is necessary or even applicable for a specific code segment. And if it is, it must understand the connection between the variables and decide whether they should be private to each thread or shared. So in our initial attempt to showcase the potential of using language models, we began by examining whether a language model can effectively classify the necessity of OpenMP and its clauses. To do that, we fine-tune a transformer model on a portion of HPCorpus. This dataset consisting of 4 loops taken from GitHub repositories that used OpenMP, with half of the loops utilizing OpenMP and the other half are not using it. And we assume that these loops intentionally not using OpenMP as the developer was familiar with this API. This dataset was employed to train Performer, which consisting of 3 different models. The first model checked for the necessity of OpenMP, while the other 2 determine if private and reduction clauses should be used. One thing we note about Performer is that it heavily relies on the code local semantics, which means that instead of learning complex relationships between the variables, the model identifies words that belong to one of the classes with high probability, like printf, which mostly belong to the negative class, and it predicts accordingly. So in order to improve Performer, we integrated as input to the model not only the textual code representation, but also other code representations, such as AST to provide to the model structural information of the code, and also DFG to provide information about how variables interact with each other. And with this in mind, we implemented the Wampify, which takes as input the for loops with their extended scope, which we believe that can provide crucial information regarding the need for parallelization. And we also use the DFG of the code. So Wampify is using the extended scope and multiple code representations in order to predict the 3 tasks simultaneously as they are interconnected. So in order to evaluate Wampify, we used well-known numerical benchmarks such as NASA-OMP and Polybench-OMP that correctly utilized OpenMP. The results showed that Wampify surpassed Performer across all the benchmarks. And we also compared Wampify to ChatGPT on the pragma classification task. And also in this case, Wampify surpassed ChatGPT. And you might wonder, what about the pragma generation? So currently we are moving from the classification task into the generation while leveraging the capabilities of TOCompiler and Coder. So stay tuned.
Hi, my name is Nadav Schneider. I'm a master student at Ben-Gurion University. And today I'm going to talk about the second downstream task, which is convert serial to MPI code with an emphasis on domain decomposition. But first, let's dive into understanding what MPI programming actually includes. So contrary to OpenMP, in MPI programming, you have to understand the whole code. You need to decide which section to parallel and which sections to not parallel. And when you do decide to parallel, you need to select the right functions in the right locations. MPI programming is not an easy task. If we compare between OpenMP and MPI, so OpenMP is a pragma-based API, and MPI is a function-based API. And the difference is that with OpenMP, we just write a pragma above for loops, and in MPI, it is scattered across the whole code. The code structural, we have some code structural changes. And if we want to serialize the codes, in OpenMP, you just remove the pragma. In MPI, it is a bit more difficult and not clear. How do you do it? Thereby, I present 3 questions. I call it the MPI roadmap. The first question is to understand what is the scope. In OpenMP, it was for loops. Maybe right now we need to focus on the whole repositories. Maybe only on MPI, you need to MPI finalize constructs. Second, how do we serialize the codes? Do we remove MPI variables? Do we remove MPI functions? And the third question is to choose the right model. It can be a generative and maybe a classification model. Empirical is our partial solution to the whole task. And we answer these questions as follows. So we chose to focus on MPI init to MPI finalize constructs. And the reason is that the probability of having domain decomposition in these constructs are higher. Second, we serialize the codes with MPI functions removal. Note that this is not a serial code, but a semi-serial code. MPI has some code structural changes as well. So if you want to serialize the code, fully serialize the code, MPI functions removal is not enough. We chose a generative model, and we have 2 options here. We have a code completion and code translation. In code completion, we specify the locations in which we want to have MPI functions. And in code translation, we refer the semi-serial code and the MPI code as 2 different code languages, and then do a translation. Note that we ignore the arguments of the functions. We only predict the MPI functions, their locations. Yeah, so we chose the code translation. This is the architecture. This is an encoder-decoder architecture, and we also use different code representations. The data set we used is HPCorpus, which consists of 25,000 SPMD codes and 25,000 non-SPMD codes. These are some statistics. So overall, we get the code, we predict the MPI function and the MPI locations, and through that we can determine if the code can be SPMD parallelized or not. We evaluate it as a classification task since we only interested in the MPI functions. And we did it on the dataset and the 10 compiled domain decomposition codes. What next? So we want to fully generate the function, meaning generate also the arguments. And in order to do it, we will use the compiler and HPCorpus. Thank you very much.